Welcome back students, how are you all? Today we are going to discuss a new chapter, position and movement. Tessellation. You have seen many wonderful collection of tiles lining many of the walls. Tessellating pattern is like that. From a mathematical point of view, the tiles are exceptional, as they show indicate tessellating patterns. A tessellating pattern is one where all the shapes form a repeating pattern and fit together without any gaps. You can see one of the example of tessellating pattern here. Triangles. Here are some examples of pattern made by tessellating triangles. Two examples you can see here, equilateral triangle and scalene triangle. In the equilateral triangle, many equilateral triangles fit together without any gaps, and a scalene triangle. So we can say this diagram shows that it is possible to tessellate these triangles with themselves. And in the quadrilaterals, the diagram below shows some tessellations of different quadrilaterals. The square pattern is down and in irregular quadrilaterals. Does any quadrilateral tessellate with itself? Does any triangle tessellate with itself? We have to solve some problems in exercise 17.1a. This is exercise 17.1a in student book, page number 160. I am going to leave question 1, 2 and 3 because these three questions are activities. So start from question 4. This diagram shows 6 equilateral triangle tessellating. What is the size of each of the angles A, B, C, D, E and F? Look at your student book. You can see the diagram. What is the size of each of the angles A, B, C, D, E and F? I gave here the answer. In this diagram, 6 equilateral triangles are there. So each angle, in an equilateral triangle, each angle is 60 degree. So size of each angles in this diagram is 60 degree. Calculate the value of A plus B plus C plus D plus E plus F. You can find out the value. 6 times you have to add 60 degree. We get the answer 360 degree. Question 5. This diagram shows an isosceles triangle ABC. The angle at A is 40 degree. It is an isosceles triangle, so the two sides are equal, corresponding the angles are equal. So angle A is 40 degree. What is the size of angle B? Angle A is 40 degree, then angle B is 40 degree. What is the size of angle C? The sum of angles of a triangle is 180 degree. So we have to find the angle C, 180 degree minus 40 degree plus 40 degree. It's 100 degree. Question 6. This diagram shows an isosceles triangle XYZ. The angle at X is X. What is the size of angle X in terms of X? What is the size of angle Y in terms of X? Angle Y, it is an isosceles triangle. So the two sides are equal, corresponding angles are equal. X is X, then Y is X. What is the size of angle Y? Angle Y is 180 degree minus angle X minus angle Y. So we can write 180 degree minus x plus x. It is 180 degree minus 2x. The next question. This diagram shows a scalene triangle PQR. The size of angle P is A. The size of angle Q is B. What is the size of angle R in terms of A and B? The angle R is 180 degree minus A minus B. And one more question with this question. The diagram below shows triangle XYZ and two identical triangles arranged together. Look at student book page number 162. What is the size of the unmarked angle at Q in terms of A and B? Unmarked angles at Q. It is 180 degree minus A minus B. The next question, write an equation in terms of A and B for the sum of three angles Q. The sum is A plus B plus 180 degree minus A minus B. So we get 180 degree. I'm going to leave some questions. So next topic, other polygons. So far we have seen that all triangles and all quadrilaterals tessellate by themselves. However, this is not the case for all polygons. Some examples are there. The polygons tessellate. How can we decide whether a polygon will tessellate with itself or not? See exercise 17.1c in student book page number 164. I'm going to solve some questions. Question 1. Look at the regular hexagon. From your work in chapter 3, write down the size of each interior angle. You studied how to find out the interior angles of a regular hexagon. It is 120 degree. Three regular hexagons can be arranged around a point. By considering the size of the internal angles, explain why this is possible. Three regular hexagons can be arranged around a point. You know, the size of each angle of a regular hexagon is 120 degree. So the angles around a point is the sum of the three angles. We can write this as 3 multiply 120 degree. It is 360 degree. Second question. Calculate the size of an interior angle of a regular pentagon. The interior angle of a regular pentagon is 108 degree. Three regular pentagons are arranged around a point as shown. By considering the size of the internal angles, explain why regular pentagons are not tessellate. The answer here, in order for a regular polygon to tessellate vertex to vertex, you can see in the picture, the interior angle of a regular pentagon must divide 360 degree evenly. Since 108 does not divide 360 evenly, the regular pentagon does not tessellate this way. That means 108 is not a factor of 360 degree. Question 3. Regular pentagon can be arranged as shown. What is the name of the shape in the center? You can see in the center the shape is a parallelogram. Calculate the size of each interior angles of the center shape. So we want to find out the interior angles of a parallelogram. You know, in a parallelogram the opposite angles are equal. So to find out the opposite angles, the first two angles you can see three pentagons fit together, and each angles of a pentagon is 108 degree. So to find out the angle of a parallelogram, 360 degree minus 3 into 108 degree, it is 36 degree. So to find out the other two opposite sides, the two pentagons fit together. So 360 degree minus 2 into 108 degree equal 144 degree. Students, we have some more questions in our student book and workbook. Find out the answers. I hope all you understood how the shapes tessellate. Thank you for watching.